All right. So in this particular lecture, I think if you recall in the previous lecture, we talked about the sensitivity of the Schlieren, and we also talked about that what is contrast and what is called differentiation and what is background and the focal length of the Schlieren, how everything is dependent and what the knife edge does, that how it basically displaces. Uh, so are all the things kind of did in previous class. Today, we are going to take this moment and talk a little bit about the shadowgraphy mathematics in a couple of slides and show that why is it dependent on the second gradient. All. So that is what we are going to cover in this class. So this is also from Sally Bain's PowerPoint presentation, part of the CalC Tech. So if you look at the shadowgraphy in general, as we talked about before, that if this was the y and the z, there could be also an x. Now what happens is that here you have a gradient of the refractive index, but this gradient is a constant. So this is how it exactly looks. So the refractive index basically changes linearly with y. This is exactly what is shown over here. So this is the kind of the change in the refractive index shown. So what happens is that all the rays are entering into this particular Schlieren or the cross section of interest. They are all kind of shifted by the same amount. So we still get a uniform shift in the illumination. We see some shadow, but we don't get the outline of the Schlieren. Okay? As we move down the path, because of this constant gradient, all the rays shift in the same way. That is what you get here. All right. But however, if you have a situation where n is no longer a linear function of y, or in other words, this is an arbitrary profile in which n is definitely not a linear y anymore. Okay? Which in other words of telling is that let's assume that the second derivative of n is actually a constant. So the curvature of the curvature is actually a constant. So this is what you get, or the gradient of the gradient is basically a constant. So what you actually see over here is that this is a constant, okay, but not this. As a result of that, the rays gets deflected, but you get a non-uniform illumination. So variation of these gradients therefore becomes critical if you want to outline of the Schlieren, which is the purpose of shadowgraphy. So you can understand that why, if you have a uniform gradient or a constant gradient, the rays are all shifted in a very similar fashion. The outline is not very clear. You don't get an outline at all. But when you actually have the second derivative of the refractive index to be constant, or in other words, the d neta by dy or dn by dy is not a constant, you get the rays which are non-uniformly distributed, non-uniformly shifted. As a result, you get non-illumination. Now, this was from Dr. Hu's work, Aerospace, Iowa State. This is from his presentation. So this provides an idea that how the math actually works ultimately. So if I take you through it, so there is this test section. The light is coming like a parallel beam here, and say this the light pipe has got a diameter of delta y, and as it goes through this particular test section, got a width of L, and from the test section, from the middle of the test section, the end of the screen, the length is ZSC, and this is where the Z starts from, and this is where Y starts from. Okay, this is where I have fixed my axis. as a result of that, what happens is that now let's assume that these rays now gets deflected. Okay? So this is basically the deflected rays. And this is the screen. And this would have been, this parallel beam would have been the path of the light if there was no test section, if there was no density variation, no refractive index change. So this gets deflected, and you can see that there is this angle alpha by which this displacement has happened, and it has illuminated length on the screen, which corresponds to this length delta y, is delta YSC. So this was the light beam. Now this is where the light beam ends up with, and this would have been the original path of the light beam. Okay, so if you now look at the illumination of SC, okay, SC, it is equal to the delta y by delta YC. So this is delta y and this is delta YC multiplied by the initial or the incident illumination on this object, which is I naught. So you can readily see that, okay, so delta IC by delta ISC multiplied by delta YC is equal to I naught into delta Y. So it's almost like the, you're putting in a certain amount of mass flow rate to a pipe, and this is what has to come out the other end, similar to that. So what we can see over here, that what about this delta YSC? So delta YSC is actually your delta Y, okay? And there is this ZSC, which is the distance, multiplied by this D alpha. D alpha is this. Can you imagine? So this would be the additional length that that is actually illuminated on the screen because of the presence of the test object, right? So this is what you get, where ZSC is measured from the center of the test section all the way up to the screen, right? Now, if you take delta I divided by I naught, what is delta I? Delta I is ISC minus I naught by I naught, which turns out to be delta Y divided by delta Y's SC minus 1. All right. Now you substitute, do a little bit of substitution. Now over here, that what is your is the final value. So you get, this is almost turns out to be equal to minus ZSC into D alpha by dy, which is basically reflection as a function I. So basically is a gradient of deflection, or the spatial variation of the deflection with y, and ZSC is the distance at which the screen is placed, and this is equal to the relative change in the illumination compared to the initial. So this is what you get. This is the expression. Delta I by I naught is almost equal to minus ZSC alpha by y. Now, this we already know, alpha, if it is the deflection alpha, or epsilon, alpha is the same as epsilon. If that is the deflection that we are talking about, this is 1 over n into dn by dy into z. This is what we knew, right? Okay. Now, remember, this is d alpha by dy now. So alpha is itself the first derivative of dn by dy. And this illumination change is the first derivative of alpha. So in other words, if you plug this in, I delta I by I naught is equal to minus ZSC divided by n. N is basically the refractive index, multiplied by, now it is d square n by dy square into dz. All right, so as you can see, this the total deflection, therefore, function of the ZSC, where the screen is placed, and it is dependent on the second derivative of the refractive index with respect to y. So the sensitivity is therefore proportional to the index of refraction, which is 1 by n, obviously, and the screen distance ZSC, and the the integrator and the variation of the second derivative of n with respect to y. So this is in general the math behind the shadowgraphy, why it is dependent on the second derivative. And I think in these two slides, we have kind of explained that why it is not just a function of radiation of n with respect to y only, but it is the second derivative with respect to y. So that is I think its importance here, and that is essentially the math of shadowgraphy. We already did some of the math of Schlieren as well, and know that how these two methods now kind of work. Now, if I look at other Schlieren systems, so far we saw that we are using lenses mainly. So there is Z-shaped systems also. This is most commonly used technique, mostly in wind tunnels and stuff like that. And what it happens is that you have a light source and then you have a condenser lens, pass it through a pinhole or a slit, and then it goes and hits into a parabolic mirror, basically transforms this into a collimated, again, a parallel beam of light, and it passes through the test area right here, which is one to measure. And then another parabolic mirror basically, focuses it to a knife edge, which we already did earlier, and you have the camera which records the image. So this is the Z-shaped system. It is most commonly used in wind tunnels, and it uses mirrors which are much easier to manufacture, so to say, than lens, as we saw from historic reference. Also, there are other type of systems like double path systems, okay? Where you use a prism, basically, and a knife edge. And this is basically a mirror prism combination and the object there. This is essentially done for off-axis measurement. And then you can also use coincident kind of methods where you use a beam splitter, really very similar to the retro-reflective type, and use camera filament. So these are different types of Schlieren systems. These are some of the examples. This is flow through a truncated aerospike nozzle. The very complicated structures, you can see them right here, and very fine grain structures you can kind of out. This is, for example, the shock waves of some strength which is hinging here. And this is a projectile which is fired at Mach 4.75, which is hypersonics, in reactive hydrogen-air mixture, the cyclic detonation behind the shock coming from the work of Sittl. Now you can guess Sittl's books on, on Schlieren and Shadowgraphy is almost like a Bible, so you should kind of consult them. If you do not have the book, you should get the book and study in more details if you want more on this. So you can see varieties of very fine scale to very large scale structures. The idea is the sensitivity of the system, even though when we say it, that the deflection is very small, n is only a weak function of density and all these things, even then you can get these very striking features. And with the advent of high-speed cameras and numerous other things, this has become much easier to do. These are examples of color Schlieren. So this is the color Schlieren of the Space Shuttle Orbiter in supersonic wind tunnel testing. This is again from Sittl's work. This is the color Schlieren of a gun which is firing a .22 caliber bullet. You can see the bullet moving and then the shocks. And you can also see this is the HSTTV air intake model, and you can see also the flow structures and the sharp discontinuities over here. So these are some of the examples of the color Schlieren images from different sources. So these things kind of, the kind of fidelity and the kind of things you can do with. So here, for example, you have a full-scale Schlieren where it is very large scale. This is the heat released from a gas grill. This is reading a paper, and you can on the space heater. This is when you take an ice cream, I think, off from there or something like that. You can see there are very large scales, there are small scales, there are focused, which can be done using Schlieren. This is also an example of an extra large scale Schlieren, which uses, astronomical telescope and uses the sun. And, this is aircraft and this shock waves, and you use the sun as the light source. Very interesting. So it is at Mach 1.1 using a telescope, which taken using a telescope, the sun, a cutoff field of view about 80 meters. You can imagine 80 meters. That's almost like, the distance that Usain Bolt runs, 100, fractionally below it. And you can see the kind of, rock structures on this aircraft. So these are the kind of very high, very large scale, 80 meters kind of a scale, down to, scales which are like this, okay? That you can resolve using Schlieren, large scale, medium scale, and also somewhere in the middle. These are the kind of the medium scale Schlieren that you can do, and even you can do colored Schlieren, which can give you different aspects of the measurement. So the difference between Schlieren and shadowgraphy, let us kind of, read it once again. That Schlieren is used by a focused image formed by a lens, and shadowgraphy is not an image, but a shadow. In some cases, for shadowgraphy, you don't even need any optics, it's a screen. And this requires the cutoff of the refracted light by using the knife edge. Here, there is no cutoff of the refracted light. You can see there is a focusing. Here, you need not do any focusing at all. This requires a cutoff. This does not require a cutoff. And the illuminance level actually depends on the first order derivative of the density with respect to space, either with respect to x and y or both. This responds to the second spatial derivative, which is the dou square rho by dou x square or dou square rho dou y square. The Schlieren image displaces the deflection angle, which is E. The shadowgraph will displace the ray displacement. This is usually the Schlieren is usually more sensitive in general. Shadowgraphy is less sensitive, except for very special cases like shock waves, because, as I told you earlier, that because it is dependent on the second derivative, you need the gradient of the refractive index to vary very sharply, which is the case in the case of shocks. Therefore, it is more sensitive to those kind of features rather than where the density is more gradual, and therefore the second order change is much less sharp or more gradual in that case. So therefore, shadowgraphy does a very good job in those cases. And it is more difficult to set up because you need lamps, mirrors, lenses, and whatnot. This is extremely easy to set up. As I said, that it need not even have an optics. And we saw the math also. This is fairly routine. So shadowgraphy can give you a preliminary idea of what is going on, and in case of shocks and other cases, it can give you some idea about what is going on. But Schlieren is something that you should be using if you want to get more fine scale, detailed features of the flow. So that is what is actually cases. But shock can use both. Okay, so some of the important equations comes from Sally Bain's work. These are the things that when you want to set up a Schlieren, what are the things you do? So for example, here is lens 1, here is a knife edge, this is lens 2, and this is the object. So, and this is the light that's coming in. So if you use a Gaussian lens equation, then 1 over x1 plus 1 over x2 is equal to 1 over f1. And 1 over x3 plus 1 over x4 is equal to 1 over f2, second lens. So now if you take magnification into consideration, so first magnification here, L1 divided by y naught, this one, okay, is equal to minus x2 divided by x1, right? And similarly, YL2 here divided by YL1, because now this is the magnification that's happening, is minus x4 by minus x3. A fairly simple equation. So the total magnification, which is YL2, final image, divided by the original image, that is given as x4 into x2 divided by x3 x1. So x4 into x2 divided by x3 into x1. So this is the total magnification. Now for a real image, okay, x2 and x3 are greater than 0. Okay, so this leads to x1 must be greater than f1 and x3 must be greater than f2. So the table size, when you are setting up this experiment, it has to be that x1, x2, x3, x4 must be less than L. So L is the size of your optical table where you are going to set this entire thing, right? So the equations continued. So therefore, you, in order to set up this Schlieren setup, you have to obey these relationships. 1 over x1 plus 1 over x2 is 1 by f1. And 1 over x3 plus 1 over x4 is 1 by f2, where x1 is greater than f1 and x3 greater than f2. And magnification is given as x4 into x2 divided by x3 into x1. All the details are labeled here, again from Sally Bain's work. And sum total of all these xi's has to be greater than L, the total. All right. So these are the important equations when you put. Remember, the knife edge is placed as f1, which is the focal point of the first lens. Okay, and then you form an inverted image here at x2, and then you form the final image at IL2. Right. Now, some simple setup instructions that one can do, again from Sally Bain's own work. First step, you need to calculate the required distance between the object, the Schlieren lens, the focusing lens, the camera, based on the equations that we just now did. And then you set up the light source, flat mirrors that are needed, the test sections with windows, and have it in place. Then step 3 is set up the laser in a place where the camera will go, then turn on the laser and ensure that the beam is straight in both the vertical and in the horizontal direction along the optical axis. Then step 5 is you adjust any mirrors on the side, on this side of the setup, to direct the laser to the test section, and you try to keep the laser dot as close to the center of the mirror as possible. If there are windows on the test section, check for reflection, make sure that the laser is perpendicular. Okay, and there are certain tips which you can read. Okay, these are all important and good information how we set up. Okay, so you are setting up, this is the side view, this is the top view, and how you are going to set up the experiment, and so on. And so after this, you adjust the mirrors on the light source to detect the laser beam to the light source, ensuring that the beam stays at the same height and it is centered on the mirror. And then you adjust the height of the light source. Okay. Then you remove the cover of the light source, make sure it's unplugged so that you can filament. Then use the controls on the light source to move the filament of the bulb. Laser light hits the center of the filament of the bulb, and you check for reflection. Then once all the alignments are done, then cure all the optics. Basically, you have to screw them in onto the optical breadboard, and one by one add lenses to the setup. And once the alignments are very important, as we say, a little bit, a few degrees off here and there, or a little bit of a distance here and there is going to ruin the entire measurement, because it's highly sensitive because of the weak function that rho is with respect to refractive index. And then replace the laser now with the camera, place the knife edge, approximate location, and turn on the light source. And then you do some in situ adjustment so that things are in place. And Sally Bain says that after this, work begins. And my students also say the same thing, that the real work begins after this, where now you have a task on our hands where you actually ready to get the measurements and try to fine tune till this measurements kind of perfectly aligned with the whole thing. So I think in this particular lecture, what we have covered is that we have gone through some of the details, man. Just a quick recap. We started that this is how the Schlieren principle works. What is the gain and what is the contrast and what is the sensitivity. We also saw that what is the math of the shadowgraphy setup. And then we also saw other Schlieren systems, the kind of systems that are routinely used. We saw some very cool examples of small, large, very large kind of Schlieren systems, especially this one takes the shocks for say 80 meters. We saw the differences between the systems. And then we saw the important equations that are needed to set it up. And then certain tips which comes from the Galset that how the system should be set up. Honestly speaking, these are still functions of, trial and error and a little bit of a hands-on experience, but there are certain protocols that you should follow. It requires very careful alignment because without alignment, the things are not going to work. So, and it is very sensitive. So you have to have a very good, have a lot of patience. And then only you can record images which are like this, which shows structures of different length and okay. So we end this lecture here. In the next lecture, we are going to start looking at that how Schlieren or the how the Schlieren can be used for tomography as well. So these are called background-oriented Schlieren technique, which basically is pioneered by many people, but among them Dr. L. Venkatkrishnan is one of them, and Mayer, so from DLR. So they are the ones who kind of proposed some of these methods, and these are exemplary methods. And they use some of the concept of the PIV and uses it here. It's kind of very interesting. Okay, so I think now you got a reasonable idea and the reasonable idea of the math and the reasonable idea how to do Schlieren. Now we will see that how you can use background-oriented Schlieren to measure the density fluctuations, and so that would be, and then it can also lead to tomographic measurement as well. Okay, so with this particular note, we end this lecture over here, and we will see in the next lecture, which will be probably the last lecture on the Schlieren technique, so to say.